Hi everyone. So in this video, I'm going to go over the second practice quiz. So it says in the following fictitious reaction, 1.5 moles of A2 is reacted with 2 moles of B and 2.5 moles of C to form the products. What is the limiting reagent? Circle your answer. Okay, so this is a limiting reagent problem. This is a Gen Chem problem. So if you notice here, we have two products, and it doesn't actually matter which one you pick, just be consistent. So what I'm going to do is I'm going to convert moles of A2 to moles of BC. Okay, so this one to this one. I'm going to repeat for B, moles of B to moles of BC, and moles of C to moles of BC. So as long as you pick one of the two products, you get the same answer. So in this case, they're both 1, so it actually wouldn't matter. But if this was a 1 and this was a 2, then you just have to pick one of them. So let's take a look at this here. If we have 1.5 moles of A2 times, to convert from moles of one compound to moles of another compound, we use the balanced chemical equation. We want to get rid of A2. There's 1 mole of A2 on the bottom. The 1 came from here. And then 1 mole of BC on the top, which will give us 1 over 1, so just 1.5 moles of BC, because this is just 1, so you get the same number. Let's do the same thing for B. So we're going to go with 2 moles of B times, we're going to put 1 mole of B makes 1 mole of BC, and we're going to get 2 moles of BC using our 2 moles of B. So right now the limiting reagent would be A2 if it was just A2 and B, but we got to check C as well. So in this case we got to check C, and we have 2.5 moles of C times, in this case there's 2 moles of C for every 1 mole of BC. So it's always 1 mole of BC on the top because there's BC. And again, you want to go to one of the products. Either of the products, it doesn't matter, but make sure you pick one because these don't necessarily all both have to be 1. So when you do this, you do 2.5 divided by 2, which is 1.25 moles of BC. So the one that makes the least number of moles of BC is going to be the limiting reagent. So in this case, the C is actually your limiting reagent in this reaction. Number 2 says, in the reaction, 4.7 grams of product was isolated. If the theoretical yield was 8.4 grams, what is the percent yield? So the percent yield is equal to the actual yield divided by the theoretical yield, and then because it's a percentage, you multiply by 100. So basically it's the part divided by the whole. The part you actually got divided by the whole, the theoretical yield, the amount you should have gotten, times 100. Now I realize in the actual lab sometimes you get above 100% yield because there's still solvent or it's still wet or whatever the case may be, but in this theoretical problem we probably won't. So let's see. We got 4.7 grams of product isolated. The isolated product is the actual yield. Then the theoretical yield is labeled as theoretical yield, so that's pretty easy. We put that one on the bottom as 8.4 grams, and then we multiply by 100. When you do that in a calculator, you get 55.95%. This is 2 sig figs, this is 2 sig figs, so rounding to 2 sig figs, the best answer here is 56%. All right, this question says, a student completed the ketone reduction reaction shown below using sodium borohydride as a reducing agent. The product was isolated and the IR spectrum was collected. So we started with acetophenone and we made phenylethanol, 1-phenylethanol. So this basically, we went from a ketone to a alcohol, to an alcohol, I should say. So before we read the answers, okay, let's just read the question and then we'll look at the IR spectrum. It says, does the IR spectrum collected support the conclusion that the product of the reaction is pure? Does not contain any starting material. What is the major IR spectrum evidence that supports this conclusion? Circle your answer. So the first thing we want to do is analyze the spectrum for different types of bonds. And this one here is going to be your OH. This broad peak, or above 3200-ish, is going to be your OH. This is your CH aliphatic, okay? And this is your CH aromatic. Then finally, we have this peak around 1750-ish. This is your C double bond O. So you do need to remember your IR peaks, which was the kind of the major focus of the last, one of the major focuses of the last quiz. So this is basically what we see. Now let's look at our molecules. Well, if we look at our starting material, what is identifiable about it compared to the product? Well, if we look at the aromatic ring, that's not very identifiable. So this one, not super important, because this one has an aromatic ring and this one has an aromatic ring. What about the CH aliphatic? Well, if we look at the CH aliphatic, this one has it and this one has it. So, in fact, this one has two. So this is not very identifiable, okay? What about OH? Well, if we look at OH, our OH is only in our product. So this is a fairly good indication that we have our product, because we do see an OH. But what about C double bond O? There is no C double bond O in our product, and there is C double bond O in our starting material. So this means that we have starting material. So does the IR spectrum collected support the conclusion that the product in the reaction is pure? The answer is no, it's not pure. There is starting material here. How do we know? Because of the presence of this C double bond O peak somewhere around 1700, 1750. So we'll go with D being the answer. I will point out to you that this is like one of the most important things you can get out of these lab classes. How do we interpret the data that we get to draw conclusions about how our reactions went? All right, if you're a doctor, you get data from patients and you have to interpret what might be the condition the patient is suffering from. And this is used in all kinds of fields, data, and then draw conclusions from data. So essentially, you could get smarter and better at solving problems by practicing such things, and organic chemistry lab is a great, and lecture 2 are a great place to practice. Oops. So this one asks us to actually write a mechanism. It says write the mechanism for the ketone reduction in the reaction shown below. Okay, so this is the reaction you guys did. So we have acetophenone, which looks like this. All right, and this is a methyl group. This is a CH3, not an H. Said another way, this is a ketone, not an aldehyde. All right, so we basically have this. And then we have NaBH4. So if we look here, boron is quite strange, and Katie, who sent you the emails, is an expert on boron chemistry. Okay, but I'm going to do my best here to talk a little bit about this boron, the sodium borohydride reagent. So if we look here, all right, this is a bit strange because boron doesn't usually like to have an octet, and in this case it actually has an octet. So another way, boron likes to have 3 valence electrons, and here it has 1, 2, 3, 4, because formally half of these belong to it. This makes this boron minus charged. That's why the counter ion here is a sodium. Now if you look at this, this means that this is kind of the opposite of an acid, if you will. Not in the way the base is the opposite of an acid, but yeah, you could think of this as a base as well. But acids donate H+. If this were to donate H+, this would put a lone pair on boron and make it 2-, which would be even more unstable. So this is actually a source of H-. Now free H- probably doesn't really exist, but this is a source of H-. So if you have H-, you have to think on this molecule, what's the plus part? Well, we could draw a resonance form of this where we drew this double bond up here and had now 3 lone pairs on oxygen. There are currently 2, they're not shown, but there's 2 lone pairs to fill the octet. If we put a third lone pair up here, this is minus and this is plus. Said another way, this carbon is partially positive. Now it's not necessary that you write this delta plus. I would say you should probably write this minus, but it's probably not necessary that you write this delta plus. So what's happening is these electrons are coming in here like this, and then these electrons are shifting up here like this. And what we end up with is a deprotonated alcohol. So we have this C, which now has an H, Still has a methyl group. Remember, this is a methyl group because this is a ketone, not an aldehyde. Aldehydes have H here. All right. And we now have O, which now has 3 lone pairs and a minus charge. All right. So this is basically an alkoxide. This is a deprotonated alcohol, which is a strong base. So there could be something there. In this case, we have ethanol, so I'll use ethanol as my source of a proton, which is a protic solvent. Okay, so this could grab this proton from the ethanol, and then that could go there. All right, this is just one source of protons. Protons often are thought of as just in solution. This probably isn't 100% pure ethanol. There's probably some water in there as well. So basically, if you use water, that's fine as well. All right, so we have this. We get this, now bonded to OH. H, this H came from the borohydride. All right, and then we still have the methyl group here. And if you want, you could have CH3, CH2O minus as the byproduct, okay, of this reaction. But for the main organic mechanism part, you need to remember that this in borohydride reacts like H minus, attacking the carbonyl carbon. It does not act like H plus and attack the oxygen. If you put a strong acid in here, it might be a different story, although a totally different reaction will occur. All right, so that is basically that. So another data interpretation question, another excellent question of looking at data and interpreting what it means. So let's take a look at this. It says the progress of a reaction is monitored using thin layer chromatography TLC. At some point during the reaction, the following TLC plate was spotted with the standard solution of starting material, a standard solution of product, and the reaction mixture. The plate was eluted with a nonpolar organic solvent and visualized using a UV lamp. The plate below shows the results. Okay, so in your labs, we tell you reflux this thing for 45 minutes. All right, that's what you did most recently this week. But in real life, we often don't know how long a reaction is going to take. So we monitor reaction progress using thin layer chromatography. This is very common. So it says, based on the TLC results below, should the reaction be stopped? Why or why not? Circle your answer. So if we look here, we could say the starting material is more polar than the product. But that's not really what matters in this monitoring system. And you guys got an opportunity to do this in one of your labs. What matters is that we have starting material in our reaction mixture. How do we know? We know because we get a spot that's got the same retention time, or RF, excuse me, the same RF as the starting material. So this indicates there's starting material in our reaction mixture. But there's also product in our reaction mixture. So we have both starting material and product. It's not uncommon for a reaction mixture to have both. Well, what does this tell us? Well, if we still have starting material in our reaction mixture, it says it's at least worth a shot to see that if it goes, to let it go longer. Sometimes reactions are reversible and you can't get rid of all the starting material no matter how hard you try, but sometimes they're not. So it's worthwhile to let this go longer and then do another TLC and see if you can get it to turn all into product and completely eliminate this starting material spot, which would be ideal. But in this case, the answer is no. There is starting material left. So it asks us if the reaction should be stopped, and the answer is no, because we can clearly see we still have starting material because we have a spot with the same RF as the starting material. There's also some product, okay, which is a good sign because that means the reaction is working as well to generate some of our product. All right, this one's asking us about melting point, which is another form of evidence that we can use to see how well our reaction went. So it says, as part of the product characterization for a reaction, the melting point of the solid product was measured using the melting point apparatus. The following melting point was reported for the product of the reaction. So this is the experimental melting point, 118 to 122 degrees. The literature melting point for the pure product is 125 degrees. Based on the melting point determined in the experiment, what do you think the product collected was relatively pure? Why or why not? So there are two things that you want to look at in melting point ranges. One, is this melting point range close to the accepted melting point? In this case, I would say this is relatively close, okay? Especially given the types of melting point apparatuses that we have, they're a little bit touchy and they heat up a little bit too fast, so they're not super accurate. So in this case, I would say this is very close. The other thing we want to know is what is the range? And I would say for our melting point apparatuses, this is a fairly narrow range. So it started melting at 118, it finished melting at 122, especially when you're heating it up quickly. All right, this is a fairly narrow range. So I would say yes, the experimental melting point is a narrow range close to the expected melting point. All right, it's not perfect, but it is a relatively narrow range and it is relatively close to the expected melting point. Now, if this was like 90 to 110, then you would say, okay, now it's a broad range and it's not really close to the expected melting point. And they usually go hand in hand. Usually, if it's far away from the expected melting point, it also has a broader range, because if it's impure and it's a mixture, it's not all going to mix, or it's not all going to melt at the same time. It says, what is the major product of the electrophilic aromatic substitution reaction of the aromatic compound and some fictitious electrophile E+? Circle your answer. So in this case, we have a methyl group. A methyl group is a weak activator and an ortho-para director. And in the next question, we'll get into the details of why, because we're actually going to show the mechanism. So I'm not going to go into the details of why this is an ortho-para director and an activating group. Some other common activating groups are OH and OCH3. So these are common activating groups. Deactivating groups and methyl meta directors tend to be things that contain carbonyls. So you could have an aldehyde or a ketone, stuff like this. These tend to be beta directors, and these are the main groups that you saw in the lab. So alkyl groups, OHs and OCH3s, and then carbonyl groups are the main ones that you saw in the lab. There are others, and look to the textbook for all the other examples. There's a much more extensive table. It's not much more extensive, but it's got like 4 or 5 more examples. Okay, so in this case, we have an ortho-para director. So if we look here, we have, remember that this is ortho, this is meta, this is para. Here we have para, so this seems like a good possibility. This one is meta, so that's not a good possibility. This one, we didn't even get the electrophile to add, so I don't know how this is an electrophilic aromatic substitution. It's not, right? We just got the starting material back. That means the reaction didn't work. And here we again have meta. Remember that it's ortho-para meta, but it's also ortho-para. Sorry, I said that wrong. Ortho, meta, para. It's also ortho, meta, para. So this is also ortho and this is meta. Said another way, there's 2 meta positions and 2 ortho positions. So this is not a good answer as well. So the answer here is compound A. And again, if you stick around for the next question, we'll go into why this thing is going to be a ortho, para director. All right, so it says, consider the EAS reaction below. What position, ortho, para, or meta, will the fictitious electrophile add to the aromatic ring? And again, this is exactly the same as the previous question, in the sense that we have an electrophile adding to toluene, and we have an electrophile adding to toluene. So it wants us to draw the resonance forms for the ortho-para attack here. So in the previous question, we said this is going to be either ortho or para. So now we need to show why based on the resonance forms. And specifically, I'm going to do para for the only reason being that that's the one that's here. It doesn't matter. It's the same for ortho. So here's what we've got. We've got our toluene ring, like so. In fact, just to be exactly the same, I'm going to draw exactly as it's up there. It doesn't matter which way you draw it, but I'm going to draw exactly as it is up there, just to eliminate some confusion. So don't forget, this is a CH3, okay? And then I'm going to draw the double bond there, there, and there. So the alternating single and double bonds. And in this case, we have our electrophile E+, okay? So the nucleophile here is going to be the pi bond, and it's going to attack the E+. Well, what do we get? we're going to get some resonance forms. So I'm going to draw this thing. All right, so the first thing that we get is we get this adding in the para position. Now, what else is here? Well, there's one H on each of these, so this still has an H. This also still only has one H. So if you look here, this one's only now got 3 bonds because it still only has one H. It had one H before. It still has one H. I'm not going to draw it because it's going to get in the way. But there's a plus charge right there. Okay. What about the other 2 double bonds? Nothing. All right. Nothing special about those. Nothing happened to them. So this double bond broke to form this new bond to the electrophile. Said another way, this bond becomes this bond. The electrophile is then attached. There was previously an H here, so now you have an sp3 carbon. All right, it's got 4 bonds, it's neutral, it's good. This one only had one H, so this one only has now 1, 2, 3 bonds. This makes this plus, which is a carbocation. And as you know, aromaticity is strongly favored. So something is going to come and pull this proton off and regain aromaticity. But in this case, we're asked for the resonance forms that explain why this attaches in the para position. So what happens? Well, this bond, okay, can go like that. All right, and when it does, it resonates. Okay, we still have the E, we still have the H, but now the double bond is here. Nothing happened to this double bond. It's still there. We have the CH3 here, and we have the plus charge right there. Okay, and if we draw it one more time, okay, now this bond goes there. What we end up with is the ring again. Still the E, still the H, nothing's happening down here. All right, still the CH3, nothing's happening up here. All right, and this time, this double bond is still here. This double bond moves here, and the plus charge moves here. So these are the 3 resonance forms. Again, the next step of the reaction is something comes along and grabs this H. The question is, why in the world is this favored? Well, the reason is, if you recall, a CH3 is a small electron donating group. So this weakly donates electrons. Well, what is a positive charge like? A positive charge likes additional electron density. And a methyl group is a weak electron donor due to a process called hyperconjugation that we don't need to talk about here. You just need to remember that this is an electron donating group. It's not as strongly donating as your OH or your OCH3, but it is electron donating. So in this case, having this positive charge adjacent to your electron group is favorable. If you redraw this, and I'm not going to do it for you, but if you draw this in the meta position, so if you have the E attached here, and then you initially get the positive charge, I should draw it on this one. If you have the E attached here, and initially the positive charge is here, if you resonate that positive charge through the ring, you'll still get 3 resonance structures. But what you'll notice is the plus charge will be here, here, and here. That positive charge will never be stabilized by the electron donating methyl group. So in the ortho and para positions, we get the positive charge stabilized by the electron donating group. In the meta position, we do not. And if you draw it here, you'll get the same thing. In fact, if you draw it here, the very first one, we'll put the plus here. So then that is stabilized. So in ortho and para, it's stabilized, and in meta, it's not. I hope that helps to explain this. I'm not actually writing it out. I'm trying to explain it, by talking. Thanks for watching the video, and I hope you found it helpful.